First, we'll use what's probably the simplest method. Recall that the reason that a trivial parallelization didn't work was that the read, modify, write operation that we needed to increment a bin was actually three separate operations: a global memory read, a local increment in a register, and a global memory write. What if we could make this read, modify, write operation here actually be one operation instead of three? If it was only one operation, it could not be interrupted by another thread. Now, we call such an operation atomic. And as we learned last unit, modern GPUs support atomic operations to memory. What the GPU does, in essence, is locks down a particular memory location during the read, modify, write process so that no other thread can access it. This is a simple change in the code. So we're only going to change one line in the code. Here's our naive histogram. Here's this new histogram that we're doing. And you notice we're only going to change the last line. We're changing this simple increment here to an atomic increment. It's a simple change, but let's see the effect. So now we're going to run the histogram program using simple histo instead of naive histo. And we see when we do that, we get the expected 4,096 elements per bin. Great news. Now, the disadvantage of this technique is that it serializes access to any particular bin during the atomic operation. Many threads might want to update that bin, but only one thread at a time actually gets to do so, and so the others have to wait. This contention for the atomic will likely be the performance limiter in any histogram code. So let's say you have 1 million measurements with which you'd like to calculate a histogram. You can choose to have 10 bins, 100 bins, or 1,000 bins in your histogram. If you use the atomic method, which will most likely run fastest?